two classes. Any question? So these are the steps which you can easily follow, and you can convert the logic to nor or like that. Oh, some problem today. Anyway, I'm keeping these slides and I will upload it. Okay. So once the network is little okay, I will upload it. Nothing to worry. Just remember that this slide, 14th of September, we have not uploaded. So anyone, any question? अरे कम से कम हाँ ना तो बोल लो.
No,
Anyone,
sir.
any question?
No, sir.
No, sir.
No, sir.
So I'm just sharing one definition now, and this definition will be used in our today's class and the tomorrow's class. So these two definitions will be used today, and in some cases pull-up registers or pull-up network will be used. Okay. So I'm starting with the topic for today. Now, in the first semester, in the first semester, you have studied some basic of transistors. So let me ask you a small fundamental question. Now, if someone asks you what is common between them, then what will be your answer? I've given you 5 options here. I've given you 5 options here: diodes, BJT, FET, MOSFET, and SCR. SCR, let me uh, write it the full form. Now, what is common between this? Chaliye, let me understand the fundamental thing. I have repeated this many times while I was teaching some of you in the first semester, and also I have talked about these devices at the beginning of the subject. So I want to know some answer from you. What is common between these devices? Or what are common between these devices? If you know more than one answer, you can answer more than one also. Yes, quickly, quickly. Time is precious.
Sir, they all are made of semiconductors.
Pardon?
Sir, they all are
Yes.
made of semiconductors.
Okay. Good. At least one answer I got. Okay. Any other answer? I need at least 5, 6 answers will be there, not one. I am asking a very basic question to you. And I've given this answer many a times. Yes. Quickly.
So all
I've
of
got
these
more
can
than.
be used as a switch.
Pardon?
So all of these can be used as a switch.
Yes. This is what I was expecting. So can you please repeat your name?
So Divyanshu Patel.
Pardon?
So Divyanshu Patel.
Ah, good. Thank you, Divyanshu. I was expecting this answer from all of you. So let me just little bit elaborate it. So remember this answer. Whenever you are given this question, you should have the answer that these are. Let me write something extra information to you. Number of PN junctions are different. One junction device, two junction device, three junction device. Okay. But one thing is common. They are switches. And we can say that they are having high speed operation as compared to manual switches. So we are using this diodes, BJT, FET, MOSFET, or even thyristor as a switch. And we calculate this speed of operation. We can use either the word flops. I hope you are familiar with flops, or uh, the frequency, that is megahertz or gigahertz or terahertz, like that. So they are measured either in terms of flops, how many flops, or the frequency of operation, megahertz, gigahertz, terahertz. We say that yes, this is the speed of operation of this devices. So when there's a switch, it has got two states. Of course, you will come across some switches which are tri-state switches. We'll talk about them some other time. There are tri-state switches also. Okay, so normally a switch has two states, and these two states can be defined as on and off, or other ways we can use the word high low, or 1 0, or 0 1. Either way, this is for positive logic, and uh, this is for negative logic. So these are some of the options we have in a switch, and we represent the state of the switch by these terms. Then, just for our information, there are tri-state switches. In this tri-state switches, there is an option enable, disable, and based upon this enable and disable pin status, the output will change. So in many cases we go for tri-state switches also. They are widely used in digital applications. Okay, so keep in mind switches have got two states which can be represented by on and off, high and low, 1 and 0, or 0 and 1. Whether we use positive logic or negative logic, that also decides how to represent the status. Now let us focus our study to a very narrow area, that is MOS. When we talk about MOS, we have got two options: basic, NMOS and PMOS. NMOS and PMOS, this depends upon the type of channel used. So if I'm using N-type channel, I will say that it is NMOS. If I'm using P-type channel, then I will say that it is PMOS. And already in the first semester basic electronics, you have the basic idea, and then Lal sir will talk about this MOS structure in detail when he will teach you the MOS after the transistors. Okay, so let us just have a basic idea about the structure. So when I am talking NMOS, I have got a gate, and somewhat we represent the symbol like this. Somewhat we represent a symbol like this, and in this symbol, this is our gate terminal. Then we have got a drain terminal, we have got a source terminal. Then there is a option for substrate, and that is connected to the body or earth. So normally that body is earthed. So uh, but when we uh, represent it, we use somewhat a symbol like this. Normally the substrate is not shown. You have also studied in the first semester the cutoff stage, the saturation stage, okay, for the and the active stage for this MOS. Now, can someone tell me why MOS is preferred over BJT and FET? When we are talking about these transistors as a switch, we prefer MOS. We prefer MOS because of the high speed of operation. So the speed of operation of MOS is high as compared to BJT and FET. That is true, that the speed of operation of MOS is high. Then also we talk about the gain bandwidth product. We talk about the input impedance and output impedance. So these are some of the parameters that we consider before picking a particular device. So we go by MOS. So MOS is preferred because of the high speed of operation, because of the better gain bandwidth product, and because of its high input impedance and low output impedance. This is the reason or these are the reasons for which a MOS is preferred. So let us talk something about PMOS. Now when we talk about PMOS, means P channel MOS. We represented this with symbol somewhat looks like same. With a difference. What is the difference? We put a bubble here. We put a bubble here. So the modified or simplified version will be, if I am finding a bubble, I will assume that it is a PMOS, and if I am not finding a bubble, then So the two symbols are differentiated like this. Again, here one more thing is to be noted in the PMOS, that so this is the characteristic of PMOS. But on the other hand, when we talk about NMOS, why I am talking all this? Because we are going to design the NAND gate, AND gate, OR gate, and NOT gate using CMOS logic. So since I'm going to explain them, I think this basic information is essential. And with this basic information, we can proceed. So let us summarize it again. This is fifth slide. I will try to save it once the network is okay. We are facing some network issue for past couple of days. So summary of PMOS and NMOS. What is the summary? Let me just draw it. Our gate, drain, and source, and you can see here the source is connected to ground. So we can say that Vs is equal to 0 volt and here some Vg. Similarly, when we talk about any question, anyone, any question? Yes, please. Anyone, any question? जो कुछ लिख रहा हूँ कुछ समझ में आ भी रहा है कि नहीं, नहीं आ रहा तो पूछिए कम से कम. Yes, ladies and gentlemen. हाँ ना तो कम से कम बोलिए.
हाँ सर, समझ आ रहा है.
So let us create some logic gates using this NMOS. Or let us use the general word. Now there is a typical thing that has been noted, and that is for the transistor as well as MOS, it is valid. What we have noted is that there is a phase shift of 180 degrees between the there is a phase shift of 180 degrees between the input signal and output signal of a transistor. Now this typical observation is now an advantage for me. So what I conclude? What is my inference? transistor can be used as a NOT gate. See how beautifully we have used this feature. But it means that if this is my input signal, then this will be my output signal. And that is what we need. We need a NOT gate. So this characteristic feature of a transistor or a MOSFET, it is same that there is a phase shift of 180 degrees. तो अगर आप एक ट्रांजिस्टर में साइन वेव एज इनपुट देंगे और आउटपुट कंपेयर करेंगे, तो आप जब इनपुट आउटपुट को प्रॉपरली कंपेयर करेंगे तो आप देखेंगे कि उसमें 180 डिग्रीज का फेज शिफ्ट आ रहा है. तो वो फेज शिफ्ट आपको मदद करता है नॉट गेट में. अब हम इसी बेसिक फीचर को यूज करेंगे नॉट गेट के लिए. So this is our NOT gate. So if I simply use MOSFET, anyone, P type, N type, doesn't matter. थोड़ा बहुत कनेक्शन में फर्क आता है, otherwise it's okay. So we can now clearly see that if I am using a single piece of FET, I can use it as a NOT gate. So I am not proceeding further because 2 minutes are left. I will talk about these things tomorrow, how to create AND gate, OR gate, NOT gate, the 6 type of gates using our PMOS as well as NMOS. Any question from your side? We have 2 more minutes. I'll be happy to answer your questions. I'm showing all the slides one by one. We started from here. Here I have given the basic hint how an AND OR logic can be converted to NAND logic and an OR AND logic can be converted to NOR logic. This I have explained here. Then I talked about this, the definition of pull up register and pull down register. Then I talked about the switches and how the switches can be used. Then I talked about the basic concept, how the switches are represented, the PMOS edge switch, when it will be low, when it will be high. We talked about this summary. Then we noted that there is a basic property of MOS that there is a 180 degrees phase shift between input and output signals. And finally, the NOT gate. So we remain here today, and tomorrow we will see that how the 6 logic gates can be constructed and what is CMOS. Thank you.
Thank you, sir.
Thank
Yes,
you.
sir.
Thank you. Thank you.